Hello and welcome back for another engineering mechanics tutorial on differential connections. This time we'll make it a little bit harder by introducing a triangular distributed load. So in this session we're going to solve this simply supported beam and find the shear and bending moment diagrams using differential connections. This is a little bit more complicated than the previous one we did because as we can see here we have a triangular distributed load, which means that our load already itself is a function of x. So you can see here it's a simply supported beam with a pin support at A, a roller support at B, a total span of 12 meters, and a distributed load that goes from 10 kilonewton meters at A to 0 at B. So the first thing we're going to want to do is we're going to find the reactions. And we'll do that just by using the three equations of equilibrium because this is a 2D problem. So I'm going to put here quickly the directions of the reactions. Remember, no directions, then any numbers and signs that you get are meaningless. So starting off with these directions, the sum of forces in x has to equal 0. So we can see that we've got AX plus nothing else in the horizontal direction, so that equals 0. Then we're going to do sum of moments around A equals 0, and in that case I've got BY times 12, and then I've got this distributed load. Now remember, distributed load, the area gives you the equivalent load, so in this case it's minus 10 times 12 over 2, and that gives me the force. Okay, so remember area is force. And then I've got the lever arm, and I know that for a triangular load, the centroid, or where that equivalent load goes, is always going to be 1/3 and 2/3 of the length. So in this case, I've got 1/3 of 12, and that gives me the distance. Nothing else contributes to moment around A, so that equals 0, and if I sum it all up nicely, I get that 12 by equals 240, and therefore by equals 20 kilonewtons. And last but not least, sum of forces in the y direction equals 0. So I've got AY plus BY, then minus that triangular force, which, as we said, the force itself is the area. So 10 times 12 over 2, nothing else, so that has to equal 0. And I get that AY equals the total distributed load of 60 minus BY, which is 20, and that gives me 40 kilonewtons. So at this point, I can replace those supports with the actual forces. So let's quickly do that before we continue. So I've got 40 here and 20 here, and they both add up to the whole of that distributed load, which, as we just found, is 10 times 12 over 2, so 60. Now the next thing we want to do is we want to find Wx, so the function of that distributed load. Now we do know that it is a linear line, so it will look something like this. W of x is ax plus b, right? That is what a distributed line would look like. Now we have two known points, and they are when x equals 0, the load equals 10, and when x equals 12, the load equals 0. And we'll just substitute those points in to find out the function of the distributed load. So substituting 1 in, I get 10 equals ax plus b. X is 0, so that is a times 0 plus b, and therefore I found that b equals 10. So I can write out my distributed load now as ax plus 10. Now I can substitute in that second point. So when x equals 12, when I'm at point B, w equals 0. So 0 equals a times 12 plus 10. And therefore I can find out that a equals minus 10 over 12 or minus 5 over 6. And therefore the equation for the load is minus 5/6 x plus 10. And now that I have the equation for the distributed load, I can start solving the shear and the moment. Okay, let's start by finding the shear. Now, before I start, I have drawn 2 lines under the free body diagram of my beam, just to leave space for the shear force and the moment. I know they're related, so I want to see what happens in relation to one another. And I've written down my equation here for the distributed load, because I will need that obviously to find the shear. I know that the shear is the integration of minus the load dx. So in this case, I'm first adding the minus, so I have plus 5 over 6x minus 10, and I need to integrate that according to x. And if I do that, I get 5 over 6, that's a constant. The integration of x gives me x squared over 2, minus an integration of 10, just a constant, so I just multiply that by x. And obviously, I shouldn't forget that I get a constant of integration, so plus c1. Now, we do know a few things. So we do know that when x equals 0, the shear force equals 40, right? Because when I'm at point A and x equals 0, the only shear force I have is from the reaction. And we've already found the reactions, so we know that point. I could have also gone according to point B. So I know that at point B, when x equals 12, then the shear force is minus 20. This is all according to the sign conventions that we've discussed before. So if I substitute those points, I get that 40, the shear force, equals 5 over 6 times 0, minus 10 times 0, plus c1, so c1 equals 40. And that means that the final equation for shear force is 5 over 12 x squared minus 10x plus 40. And we found the shear force. I do, however, want to look at a few points, because using this equation, I can obviously plot it on the diagram. So there are a few points that I want to see. I want to see what happens when x equals 0, so I'm at point A, and what happens when x equals 12, so I'm at the end of the beam at point B. So when x equals 12, the first two terms fall off and I get 40, just as I'd anticipated. And then when x equals 12, I get 5 over 12 times 12 squared minus 10 times 12 plus 40. And if we calculate all of that, I get minus 20 kilonewtons, as I'd expected. So let's put those points on the graph first. So here I have 40, here I have 20. And I know according to the shape, right, according to the x squared, that this is going to be a parabola. But there is one more thing that I want to find out, and I want to find out exactly when the shear force crosses 0. And that is really important to me, because I know that when the shear crosses 0, that the moment will be max or min. So just tidying up my sheet, leaving that final equation for the shear force that we need. And as I said, I want to find out where on the graph does shear cross 0? Or in other words, when does Sx equal 0? So to do that, when S equals 0, I need to solve the equation of S equals 0. So S is 0, and I have 5 over 12 x squared minus 10x plus 40. And as you can all see, this is a quadratic equation. And you probably all remember how to solve this, but x1, 2, so the roots of this equation are going to be minus b plus minus a square root of b squared minus 4ac divided by 2a, where, as you recall, this is a, b, and c. So in our case, that gives me minus 10 plus minus a square root of 10 squared minus 4 times 5 over 12 times 40 divided by 2 times 5 over 12. And if I solve that, I get minus 10 plus minus, that square root works out as 5.77 divided by 5 over 6. And so I get two square roots. I get x1 and x2. x1 works out as 18.9 meters, x2 works out as 5.07 meters. Now the first solution is not physical because it is out of the bounds of our 12 meters beam. So I know that when x equals 5.07, I cross the 0. And so let's put it on the graph, say roughly somewhere here, 5.07. At that point, the shear is going to be 0. And so the shear force is going to look something like this. Okay, you can see here a parabola starting at 40, crossing 0 at 5.07 and reaching minus 20. And here we have the shear force complete using differential connections. Now, if I'm wondering what the shape is and I can't see it directly from the equation, what I would suggest doing is taking your shear force and substituting half of that distance between the maximum and where it goes to 0. So if that's 5.07, so say roughly x equals 2.5. Now I know that if this is exactly triangular, it'll be 20, right? So if this was the shear force from 40 to 0, it would be 20. If it's over 20, then it's probably going to look something like this. If it's under 20, something like that. And if you calculate that shear force, you'll find out that this works out something like 17.6 kilonewtons, meaning it goes under and therefore the shape is as I've drawn. Otherwise, you can just use maths to interpolate the equation that you found for shear. And the very last thing that I'm going to do is find the bending moment. Now, the bending moment is the integral of the shear force according to x. And so in that case, I just take the shear force. I've got 5/12 times x squared minus 10x plus 40 and integrate all of that according to x. So what do I get? I've got 5/12, then x squared integrated is x cubed over 3 minus 10 times x. X integrated gives me x squared over 2 plus 40, which is a constant, so it gets multiplied by x, and plus c2, a constant of integration. Let's just rewrite that a bit more neatly. So I've got 5/36 x cubed minus 5x squared plus 40x plus c2. Just like before, I do know some things. So what I know is that when x equals 0, the moment has to equal 0, right? Because that is a pin support at the start of the beam. The moment has to equal 0 because there isn't any resistance to bending. And therefore, if I substitute that, so the moment equals 0, then first term is 0, second term is 0, third term is 0, and I'm only left with c2. So it's obvious that c2 equals 0, and I can write my final bending moment equation as 5/36 x cubed minus 5x squared plus 40x. And let's do a few things. Let's check that it is also 0 at the end, and let's check what that maximum moment is. I know the location of the maximum moment because the maximum moment happens when shear is 0, and I know exactly where that happens. Just making a bit of space, I want to know what happens when x equals 0. I'm expecting it to be 0. What happens when x equals 5/07? I'm expecting that to be the max moment. And what happens when x equals 12? The end of the beam, I'm also expecting 0 there. So it's really obvious from looking at the equation that when x equals 0, the moment equals 0. When x equals 5.07, I have 5/36 times 5.07 cubed minus 5 times 5.07 squared plus 40 times 5.07, and that gives me, if I calculate, 92.37 kilonewton meters. And if I substitute for the last point 12, I get 5/36 times 12 cubed minus 5 times 12 squared plus 40 times 12. And if I put all of that in my calculator, I get 0. So knowing these points, I'm going to move back up to my diagram and I'm going to enter them in. So as we said, 0 here and 0 here. And at this point, when my shear crosses 0, I get 92.37 kilonewton meters. And so my bending moment is going to look something like that. And that's it. Let's just end by looking at what we've done quickly. So the first thing we did was find the distributed load as a function of x. We then integrated it and found the constant of integration to find the shear force, and integrated one more time and got a new constant of integration to find the bending moment. And once we have all the equations, we can simply draw our shear force and bending moment diagram, especially if we know the connection between them and we know that when the shear force equals 0, the bending moment is at the maximum. And that's it. We've taken a slightly harder example, but still managed to solve it in exactly the same way. Thank you for joining me again for another tutorial on differential connections in engineering mechanics. I hope you join me again for some more structural engineering. Bye for now.